Hello everyone, I'm Tang Zhao. I'm very pleasant to be here to join the conference and present paper. The topic of my paper is detection and localization algorithm based on sparse reconstruction. Here is the contents. My presentation will include 5 parts. First of all, I will give a short introduction to Internet of Things and the wireless sensor networks. As shown in the figure, the basic construction of wireless sensor networks includes sensor nodes, sync node, and the data processing central. The sensor nodes collect physical data and transmit them to the data central. The data central plays an important role in data processing, data classification, and further data integration. In the supervised areas, the wireless sensor networks can monitor the objective effectively, while in Internet of Things, more and wider areas can be monitored. Wireless sensor networks have a high research value. It has been used in many fields, such as forest fire protection, personal health care, mechanical fault diagnosis, even in the military defense and so on. We know most applications require accurate location information, and the collected information is meaningful only when their location information is correctly designed. And it also can be processed correctly only when their locations are known. The motivation of this paper is to ease the tension that locations of nodes in the networks are estimated incorrectly when the nodes are deployed in malicious environments. In this case, the secure localization is especially important. Then we make the introduction to the network module. Before we propose our localization algorithm, I'd like to introduce the network module employed in our paper. As shown in the figure, the distance measurements of sensor networks are variables based on the received signal strength. Each anchor node provides other nodes with location reference. In the presence of the malicious anchors, DI is the distance measurement between the ICE anchor and the target node. It can be obtained based on the following formula, where AI is the location of ICE anchor, T is the target node, NI is the noise of the ICE anchor, UI is attack component. And then we make the introduction to the proposed algorithm in this paper. There is a flow chart of algorithm, including anchor node send location request, recover the sparse vector, establish perturbation module, norm constraint, gradient projection, identify the malicious anchors, locate the target anchor, extract location information, filter out malicious anchor nodes. Firstly, we establish the perturbation module. UI is a tag component between S anchor and the target node. UI is 0 when the S anchor is honest. UI is non-zero when the S anchor is malicious. The perturbation vector U is a sparse vector. The secure localization problem is formulated as sparse signals recovery problem. Then we make selection in the norm constraint. When selecting 0 norm constraint, the recovery problem is a non-complete problem, which cannot use exact algorithm. Have to use a valid approximation algorithm. When selecting two norm constraints, the solution is not ideal. When selecting 1-0 constraint, it could obtain best sparse solution. The regularization of one norm is obtained by moving the parameters on the optimal trade-off curve between two targets, the minimum values and the sparsity vector. Two non-negative vectors are introduced to build U into its positive and negative parts. With the help of gradient projection method, reconstruct the vector and make interaction search for the optional solution. The iterative process is shown in the formula. The value of the lambda k is 1 for all k, and fk is the first number in the sequence until inequality meets. After that, we fill out a malicious anchor, including determination of reference anchors and sequential probably rational testing. In the previous stage, when the value of the disturbance term of a node is 0 or close to 0, the anchor node is determined as a benign anchor node. When the value of the disturbance term of the node is not 0 or far exceeds the disturbance charging region, it is determined as a malicious anchor node. In the latter stage, we make the sequential probably rational testing. Before testing, we establish a Bernoulli random variable, Zij, for the difference information Zij of the remaining anchor nodes. When the probability P is less P0, then we accept hypothesis 0, which means that anchor is benign. When the probability P is greater than P1, then we accept hypothesis 1, which means that the anchor is malicious. Here, the P0 and the P1 are the value predetermined. We estimate the target node location. In the location algorithm based on RSSI region, the attack may indirectly affect the region by interfering the transmitting power. According to logarithmic distance model, the relationship between the received signal power and the region is non-linear. The anchor node close to target nodes is more resistant to noise. So we use the modified version of the weight least square errors to make the final calculation. The final estimate of target node location can be calculated by, where the matrix W and the B are given as follows. Each anchor node can be weighted by the variance of square root of distance measurements. We perform many simulation experiments, ran program coded with MATLAB. I will report the results. The proposed algorithm is to compare with other secure localization methods. EMDC, Enhanced Malicious Node Detection using Clustering and Consistency. GD, Gradient Descent. MINDIF, Malicious Anchor Node Detection based on isolation for rest. The evaluation indexed in the experiments includes detection accuracy and position accuracy. We consider a two-dimensional localization, in which all anchor nodes in the region are randomly distributed. Some parameters in the experiment are shown as follows. When a single malicious anchor is attacked, the figure shows the variation curve of position performance with standard deviation of the attack. The algorithm proposed in this paper. Compared with EMDC, the MLE is improved by 18.3%. Compared with GD algorithm, the MLE is improved by 16.9%. Compared with MINDIF algorithm, the MLE is improved by 13.7%. The figures show the variation curve of detection performance with standard deviation of the attack. The proposed algorithm's FPR is 0.11. The proposed algorithm TPR is 0.89. When in non-coordinate attack with multiple anchor nodes, the figure shows the variation curve of position performance with the standard deviation of attack. The algorithm proposed in this paper, compared with EMDC, the MLE is improved by 17%. Compared with the GD algorithm, the MLE is improved by 61%. Compared with MINDIF algorithm, the MLE is improved by 36%. The figures show the variation curve of detection performance with the standard deviation of the attack. The proposed algorithm's FPR is 0.11, and the proposed algorithm TPR is 0.91. So, the proposed algorithm outperforms any other algorithm of interest. In conclusion, malicious anchor nodes may tamper transmitting power and launch non-coordinated or coordinated attack to the network. Traditional localization methods do not consider case of anchors under attack. Hence, we propose this algorithm. Filter out the malicious nodes and choose successful localization for the awareness sensor networks. The contribution include the localization problem is formulated as a sparse recovery problem. The gradient projection basic algorithm is proposed to identify non-zero items and detect malicious anchors. The proposed algorithm outperforms any other algorithm of interest. Here are some references. That's all. Thank you.